Okay, so I think we can start to introduce the first talk of this session. So first of all, let me remind that we will have a talk now, then followed by a coffee break with Professor Ponton, and then following other talks. So you can start with the first one. Let me introduce Amadeus GEBAUER from the Technische Universität München, who will give a talk about a homogenized constraint mixture model for predicting cardiac growth and remodeling. So please, Amadeus.
Thank you for your kind introduction, and also from my side, welcome to my talk about the homogenized constraint mixture model for predicting cardiac growth and remodeling. I'm a PhD student at the Institute for Computational Mechanics at the TU in Munich, and this work, I have several partners and also supervisors, Martin Faller, Fabian Breu, and Wolfgang Wall. So let me first motivate growth and remodeling. They can be categorized into two categories. So on the one left side, we have atrophy. This is if the heart shrinks in size or mass, which could happen, for example, due to bed rest or a ventricular assist device. And on the other side, we have cardiac hypertrophy. And cardiac hypertrophy could be physiologic in case, for example, due to exercise or pregnancy. But, and this is the case where we are interested in most, it could also be pathologic, for example, after an aortic stenosis, we may get hypertension, or after a myocardial infarction. Pathologic hypertrophy can then result in the severe case in heart failure or arrhythmia. So the goal of our project is to create a predictive cardiac model of cardiac growth and remodeling that could later be used for diagnosis and assessment of different therapy options. So let me first briefly review some fundamentals of growth and remodeling. So I start with tensional homeostasis. Experiments with collagen gels seeded with fibroblasts, if they are loaded in a device. So at the beginning, if the length is constant, you see also that the stress is constant. But once you decrease the length, it's happened exactly that what you would also expect, that the stress also decreases, but slowly returns back to the original value, which we call the homeostatic value. And this is what we call tensional homeostasis. So we think that, or it's like common known, that collagen gels or soft tissue, living tissue, has a preferred stress state and tries to go back to this preferred state. And a mechanism that is very important to maintain or to have tensional homeostasis is turnover. Turnover is continual deposition and degradation of mass. So this is a big difference to traditional engineering materials, so that tissue is actively deposited, but also actively degraded, and that not only during injury, but also in the physiologic case. And this mainly prevents mechanical fatigue. In case of maintenance, so the mass that is deposited, so maintenance means the tissue structure and so on does not change. In this case, the mass that is deposited into the body and the mass that is degraded just equals out. In the heart, we have several different constituents. One of it are cardiomyocytes. Cardiomyocytes do not turn over per se, but there is an intracellular process that exchanges intracellular components. So turnover could there be seen as an intracellular process. The last one is the mass that is deposited into the body that cannot be stress-free. So think about the maintenance in this case here. So here we are at maintenance. If tissue is degraded under stress, and newly deposited mass is added without stress, the stress level could not be maintained, it would decrease. But as we see, it is maintained. So the newly deposited mass must be pre-stressed when during deposition. And we assume that constituents will be deposited in their preferred stress state. So let's come to how can we model those fundamentals of growth and remodeling. So one very famous model that is doing that is the constrained mixture model that was introduced by Humphrey and Rajagopal in 2002. And this theory bases upon the theory of mixtures. So the body consists of n structural relevant components, for example, collagen fibers and myocytes. And each of the constituents itself is composed of multiple mass increments that are deposited at every point in time. You'll see in this figure that at every point in time, we add new mass increments for every constituent into the body. And each of those mass increments, you also see that they are pre-stretched. So here, the deformation gradient F pre, showing that this mass here is not stress-free during deposition. Mass is, of course, also degraded over time. So the influence of the mass on the stress outcome becomes lower the older the mass is. All constituents and all mass increments form a constrained mixture. So we assume that they undergo the same elastic deformation over time. One disadvantage of this model is that we have to track all reference configuration of these mass increments, and over time that are getting more and more, and the computational complexity rises and rises. So Zyron et al. Proposed a temporal homogenization of this model in this paper here. And what they actually do is they look at the stress of the constituents and look how these stress changes due to the deposition of new mass that is pre-stressed. So here, this is the mass fraction of the new mass, and this is the pre-stress of this mass, and also the existing mass here, and the mass that is degraded under the stress that is currently there. And then we just have to define net mass production rate. So the net mass production rate is the difference between the mass that is deposited and the mass that is degraded. And we assume here a linear dependence between the current stress state and their preferred stress state. So if the current stress state is larger than the preferred stress state, then net mass is produced. If it's lower, then net mass is reduced. And for mass removal, we simply assume a Poisson process with time constant Ti. And if we combine these equations here, we can then derive an equation for the remodeling deformation gradient, which is here, and we can solve this equation at every point in time. So let's shortly summarize this method. So the reference configuration consists of n constituents that are each pre-stressed, and then we define from the mechanobiological fundamentals of turnover, we can then calculate a remodeling deformation gradient for each constituent, and then we have an elastic deformation gradient that then ensures on the one side compatibility, and on the other side equilibrium with the external forces. Growth in this model is handled with this term here. So this is a modified penalty type term that ensures that the volume change must compensate the change in mass. So what is the assumption behind that? And the assumption is that if new mass is deposited into the body, then the whole cell has to extend. So the whole cell stretch as a whole. Exactly. This could also be enforced by a Lagrange multiplier, but we use here a penalty type formulation. So let's come to the application. So I applied this model on a generic ventricle. We see that here it is loaded by we have here, sorry, let's go back. We have here omnidirectional springs on the base and springs just in normal direction on the pericardium. And we have, like in cardiac mechanics, very usual fiber distribution of -60 degrees at the epicardium, and that smoothly transits to +60 degrees at the endocardium. We assume that we have three distinct constituents that are in the first cardiomyocytes, the one here in red, with an exponential strain energy function in the direction of the fiber. And we also have a net mass production rate that, as declared vorher, the current fiber stress, the difference between the current fiber stress and their preferred stress gains us the net mass production rate. We assume at the beginning that the initial mass fraction of the myocytes are 60% and their homeostatic pre-stretch is 1.13. And from this homeostatic pre-stretch, we can then compute the homeostatic stress. Next one, we have collagen fibers with also an exponential strain energy function. We assume that they are aligned in fiber direction and in cross fiber direction. They have also a similar net mass production rate. And we assume that 10% of the initial mass fractions are collagen fibers, and they have a homeostatic pre-stretch of 1.1. All remaining constituents, we combine it into one. So all remaining cells and the elastine matrix. And we assume isotropic response also here in exponential, so that in overall we almost get a Holz-Apfel-Octen model just without the shear coupling term between the fiber and sheet direction. We assume that the elastine matrix does not remodel, and also the initial mass fraction is just a rest. So let's look at the results. We start the simulation at homeostasis. So prior to the time 0 here, there would be an algorithm that brings all the constituents into their preferred homeostatic state. This algorithm is not described here, so we assume that we already start there. So the ventricle is loaded with a pressure of 100 millimeters mercury, and at one point in time we increase this pressure by 20%, and at a later point we decrease it again to the original value. So at the beginning we see, since we are in homeostasis, nothing changes, so the myocyte stress is already at the preferred stress state, and also the left ventricular volume and the collagen fibers, the collagen mass fraction does not change, so it's at 10%. So after we increase the pressure by 20%, we see that the myocyte stress increases and then is able to return back to its homeostatic value. And this happens through the generation of mass. So we also see that the left ventricular grows. And also here, if you look at collagen fibers, we see that after remodeling, there are more, the mass fraction of collagen fibers also increases from 10 to around about 12%. And if we then decrease the pressure again, so for example, simulate that we repair the aortic stenosis, we see that the myocyte stress is for a short time lower than their preferred stress state, so mass is degraded. And then we see that it will return back to the original value, and also the left ventricular volume also returns back to almost the original value. We don't land exactly at the same volume afterwards, because growth is a very highly coupled process. So we see here a small difference, and also here in the collagen fraction. So now we look at a second case. So if we load the heart not with 120 millimeters mercury, but with 150, we will see that the myocyte stress will not return back to the homeostatic stress, so the left ventricular volume will grow forever. So we are here in a regime that is unstable. So this pressure increase was too high for the ventricle to just compensate it by growing. Probably the heart, so at this time, the nonlinear solver failed to find a new solution. Probably the heart would have failed before, so we would have seen heart failure at this patient before the simulation stopped. We did the same simulation also with the 150 increase, but for different growth parameters. So we see the higher the growth parameter, the more stable the simulation is. So with a growth parameter from 0.3 over the turnover time constant, we see that even this increase in pressure could be made stable. So let me short summarize my talk. So what we have seen, so my model is modeling the fundamentals of growth and remodeling. We try to make some fundamentals assumptions and try to model them. This model is capable to describe stable and unstable growth with the same set of parameters. So only the external forces describe whether we end up in a stable or unstable regime. Since we are modeling growth and remodeling for each constituent separately, we can also capture fibrosis. And we have also seen that this model can also show reverse growth when pressure overload is removed. Still, there are some things to do. For example, we are using very similar growth laws for collagen and cardiomyocytes, but of course, those growth laws differ. So if you want to capture concentric and eccentric growth, we probably have to use different growth laws for collagen and cardiomyocytes. And we also just use the generic ventricle and not a patient-specific and full heart geometry. And we did not couple the simulations yet with a model of short time scale. So we have not done any electromechanics or structural Windcast model to check back whether the grown configuration is still functional. And last but not least, we have not compared yet the results to longitudinal MRI data, which is a very important step. So I thank you for your attention, and I'm happy to answer your questions.
Thank you very much for your very interesting talk. So now the floor is open for questions. I already see a question by Professor Vergara, so please, Christian.
Thank you, Francesco. Christian from Politecnico di Milano. Thank you for this very interesting talk, a new perspective for growth, cardiac growth. I would like to ask you if you're planning to move towards more specific fluid dynamic quantities that could influence the growth. For example, not only a single value of pressure, but maps of pressure recovered by the solution of a fluid dynamic problem, all Walsh stresses maps, and if the fact that these quantities could be different in different regions of the endocardium is easily, your method could be easily, let's say, applicable to this case. Thank you.
So let me answer your first question. So our current plan is to look for growth laws that capture the results that are seen and also reported in literature better than our current model does. And maybe in a later simulation, we may also include some fluid dynamics. But I also showed it here. We did not include yet a short time scale simulation. So I think this would also be necessary to do that. So to just check back every few growth and remodeling cycles, whether the geometry is still capable to manage the heart function, and also whether, let me think, whether maybe the external forces also are changing due to the short timescale simulation. And your second question, I'm not sure whether I got that correctly. You asked whether the model can also use inhomogeneous parameters in the domain. Yes, of course. Maybe I didn't.
Well, now I suppose that the pressure, the value 100, 120, is an input for your mixture model, okay? But this is a scalar, okay? Yeah. I wonder if when you have a map of pressure, for example, recovered by a CFD simulation, if this information, which of course allows you to localize the growth, okay? You have region with where the growth is more important than other regions, if this could be easily applicable with your model, or if you need to develop specific models. I don't know.
What our model is, so we have a full finite element model of the left ventricle, so we can apply this pressure of 100 or 150. So we can apply at each point on the epicardium or the endocardium, so a known pressure. So this is actually currently still possible, but
okay.
We are still in a very early development of this model. So we just try the constant pressure in the whole.
Yes. But this is fine. Very, very good. Thank you.
Thank you also for this question.
Okay, thank you. So there is a second question from Hossein.
Thank you. So thank you, Amadeus. It was a great talk. So it was really interesting because my research focus is growth and remodeling. So I was able to, kind of relate with your work. So basically, my main question is that, okay, so in the constant mixture theory, each constituent basically evolve its configuration at each given time step. Is that right? And so I believe as the growth is happening, since the homeostatic configuration is evolving, so the set point for the growth or the homeostatic level for the mechanical stimulus would evolve as well. Okay, so if we assume this hypothesis is correct, how do you justify your approach where the homeostatic level in your simulation was kind of constant? And since based on if you go back in your figure, the set point level for the myocyte stress was fixed, and as the ventricle was growing, yeah, for example, the second panel from the top, you can see that I believe the dashed line is the set point, the homeostatic level.
Yes.
So it's constant throughout the whole simulation. But what I was, I don't know, what I've been seeing is that since in the constant mixture theory, each constituent is evolving, the homeostatic level would evolve as well. So it's not gonna be a constant. So what's your justification, or what's your opinion on this? That the homeostatic level in here is constant. Why is that? Don't you think you should allow it to evolve throughout the simulation?
Well, what we believe is that myocytes and collagen fibers have a preferred stress state that does not change over time. So if I just go back to this slide here in tensional homeostasis, so that were experiments that were done on collagen gels that were seeded with fibroblasts, and they have seen that this value roughly is always the same. And if you, for example, look into papers, they also reported that even this homeostatic stress on collagen fibers is even the same between species, or it's not exactly the same, but it's the same within a very small difference. So like, I think between species of elephants and mice, the difference is just with a factor of 2 point something, if I'm not wrong. So this is our justification, though, that the homeostatic value of the myocyte does not change. But still, our model is not limited to that. So if one has strong evidence or want to model like evolving homeostatic state, this is for sure possible with the model. So it's like not constrained to just have a constant level of homeostatic or for homeostatic state of each constituent.
Okay, so yeah, thank you. Yeah, because my question was based on a recent review paper by Dr. Holmes that they suggested constant mixture theory would maybe resolve the issue of capture reverse growth in LV growth and remodeling. But anyway, thank you for your answer. And can I ask, have you published this work or
no? This
not
is not published yet, but it's
okay.
planned.
Thank you very much.
Soon. Yeah.
Perfect.